Hello all, hope you are doing good. I welcome you all to the sixth lecture in this course E698M. This will be the last lecture that we will deal with quantum mechanics exclusively, but we will keep using these quantum mechanics principles throughout this course. So the last time we met, particularly in lecture 4 and 5, we spoke about particle in different potentials. So we spoke about particle in a harmonic potential, a harmonic potential has a form something of V of x is half k x square, k being a constant determined by the potential, and something of this sort, right? This is if this is x, we wrote V of x, which is a square, has a square dependence of x. So if you have a potential something like this, the potential has this kind of characteristics that as x goes to plus or minus infinity, the potential also tends to plus or minus infinity, right? In fact, it even tends quicker to infinity, but at least we know for a fact that it goes to infinity. Okay, we wrote the total Hamiltonian to be 1 by 2m p hat square, p being the momentum operator, plus mwx. You can write x as an operator as well. And the Schrodingers equation can be written h hat psi is E being the energy values psi, and in the Dirac notation it can be just written simply like this. We know that the P as an operator could be written as h cross by I d by dx, and under these definitions we introduced, to solve this simply, there are other ways to solve the harmonic oscillator which is a little bit more involved, but for the current course and for our needs for understanding the harmonic oscillator, we found it better to just introduce these two operators. A dagger was defined as root 2 h cross m omega minus I p hat plus m omega x. A was written as 1 by root 2 h cross m omega I p hat plus mwx hat. So the reason why they were defined like this was to enable us to write the Hamiltonian in this particular format, where A dagger A always turned out to be h hat by h cross omega plus half, and A dagger turned out to be h hat by h cross omega minus 1/2. If these things turn out to be true, we know that the Hamiltonian can simply be solved, because we were able to find solutions for A and A dagger, and all wave functions which were solutions to A and A dagger were also solutions to the Hamiltonian, right, as can be seen from these definitions. So we found that if we take A dagger and act it on a state psi n, it always changes this to psi n plus 1, right, where the energy of, let's say, psi n was En, energy of psi n plus 1 was En plus h cross omega, which was En plus 1, right? This is something that we knew. We knew that the energy goes linearly with the number of things, right? And we know that A dagger of, let's say, n minus 1 gave us n plus psi of n plus 1, and A acting on psi of n gave psi of n minus 1, A acting on psi 2 will give you psi 1, and obviously A acting on psi naught or the ground state is going to give us 0, right? Because A was called as a reducing operator and A dagger was an incremental operator, right? You started to increase energy with A dagger, and if psi naught is the ground state energy, we know that the energies of harmonic potentials can be written as h cross omega n plus 1, and in the ground state where n equal to 0, the energy was half. You cannot reduce it any further. This is the lowest energy of the system. So if A acting on psi naught should give us 0. If this turned out to be true, then we could, because we know the operator form of A, then we were able to find the solutions. Psi naught, one solution psi naught was or could be written as m omega by pi h bar power 1 by 4 e power minus m omega by 2h cross x square. So this is obviously a Gaussian, right? So if we take a potential of this particular form, the first state will have a wave function psi which looks somewhat like this, a Gaussian, right? So this is n equal to 0, psi of n equal to 0, right? And what happens to psi of n equal to 1? How do you find psi of 1? Is just A dagger psi of 0, right? And A dagger, we know the form of A dagger, which is 1 by root 2 h cross mw n omega, minus ip hat plus m omega x acting on psi naught, and psi naught is this expression. If we resolve this, we will get psi 1 to be A1. It will have a new normalizing constant, right? Because it is different from the previous one. We write it A1 by root 2 h cross m omega minus h bar d by dx, this is p hat, plus m omega x acting on m omega by pi h bar power 1 by 4 e power minus m omega by 2 h bar x square, right? And this will turn out to be A1 m omega by pi h bar power 1 by 4 root 2 m omega by h cross e power minus m omega by 2 h bar square into x square, right? And of course this can be normalized, and when we normalize we will find A1 to be equal to 1, and this will just vanish. Okay, psi 1 is A1, and to normalize this we have psi 1 hat psi 1 dx, which will prove A1 square will be equal to 1, which will make A1 equal to 1. Okay, so similarly we can always write psi n can always be written as 1 by root n factorial A dagger power n psi naught. Okay, so this is the general form of the any excited state of a harmonic oscillator. So if we draw the excited states of an harmonic oscillator, it will look like this. Let's say this is x and I'm plotting psi of x. We can also plot what can be observed, that is mod psi of x square. Let's say the potential is a harmonic potential, something like this. The ground state, as we saw previously, is a Gaussian. So right, this is n equal to 0, and let's say the n equal to 1 has to have one node, as we saw previously, right? This is n equal to 1. N equal to 2 will have two nodes, so it will behave like this. And this is n equal to 2. So as can be seen, let's say if this is the 0 point, psi of x square will be a much more squeezed function than psi of x, right? It is mod square. So we will have something. This is n equal to 0. N equal to 1 will have, of course, this one cannot have any negative values because psi of x square is known to be a positive real quantity. So you will have a node here. This is n equal to 1. N equal to 2 should have obviously two nodes, right? Right. So it will have nodes here and nodes here. This is n equal to 2. Right. So these are the wave function solutions for a harmonic oscillator, and it will be instructive to compare this one with the function that we have previously seen, which also has similar characteristics with potential going to infinity as at x goes to infinity, right? We saw this infinite square wall potentials. So I'm just going to keep it here and compare. So we saw this, let's say this is x equal to 0, this is x equal to a, this guy going to infinity, right? This is the potential V, and obviously as x tends to plus or minus infinity, V tends to infinity, right? And under these conditions, what were the solutions for a square wall potential? The energy values were n square pi square h bar square by 2ma, right? And psi n's were root 2 by pi sine n pi x by a. It's easy to see that for the ground state, n cannot be 0, right? For a square potential. If n is equal to 0, all you get is the trivial psi equal to 0, in the sense that there is no particle anywhere. Well, the same case for the harmonic oscillator, at n equal to 0, you do not have psi equal to 0, right? You have some solution. So let's take a look at how things are in the square wave potential. You will have this for n equal to 1, and n equal to 1 is the ground state, and for n equal to 1 you have no nodes. The ground state has no nodes for any of these solutions. Even for the harmonic oscillator, the ground state has no nodes. Similarly, for the square wave potential also, the ground state has no nodes. The first excited state, n equal to 2, for square wave potential should look like this, right? N equal to 3 should have something like this, and such, right? So it will have two nodes in this first place. In n equal to 2, you have one node here, and so on and so forth. Here the first ground state energy, of course, the energy for the square wave potential goes exponentially with the state n, right? So let's say is for as n for a square wave potential goes as square of n, whereas for a harmonic oscillator this is square wave. For harmonic oscillator you will have something like this. I think I made a mistake here, right? So this is an harmonic oscillator. It's because E of n equal to 0 is not 0 but half h cross omega, right? So this is the 0 point energy which is observed in a harmonic oscillator, whereas the ground state of a square wave potential where it is completely bound will have this kind of situation, right? The ground state has the zero energy state is still 0, and the first excited state or the first ground state will have no nodes and it will show this kind of a behavior. So it is so these are the two potentials which we saw under this condition, that as x tends to plus or minus infinity, v tends to infinity, right? So this is the both harmonic oscillator and the square wave potential has these characteristics. The second example or second set of problems that we saw where the potential at x tending to infinity or minus infinity and v will tend to 0. We saw the most simplest case in this particular example, which was the free particle case, in the sense that there was no potential anywhere. So it does not specifically mean that x tending to plus or minus infinity, the v goes to some value. V was 0 everywhere, right? And the solutions were, of course, plane wave here. Psi of x is e power I kx. And we know that the solutions of, or the eigenfunctions of the harmonic oscillator, the Hamiltonian, are not real solutions because they are not normalizable. Solutions of Schrodinger equation are not normalizable, right? In this case, you need to generate a wave packet, and these are physically realizable solutions. So any solution psi of x are basically some summation of the eigenfunctions, whereas here where the solutions, where the potential goes to infinity at some point and then stays at infinity, in the sense that as x goes to plus or minus infinity, the potential definitely goes to infinity, right? Example, the square wall potential and the harmonic potentials. So you can always find solutions such that E is less than the potential, right? Here the potential is 0, so you cannot have any energies lower than the potential. But here you can always find energies lower than the potential because the potential goes to infinity, right? And hence these solutions are called as bound state solutions. So whatever be the shape of the potential, so you can have some crazy shapes, right? So does not have to be a nice looking harmonic oscillator potential, but as x tends to plus or minus infinity, if the potential goes to infinity, you can see that you can always have some energy level E lower than the potential V at infinity, right? So that you will have some solutions which stay between some known bounds in the x and in the x-axis, or in the spatial domain if you take three-dimensional thing. Whereas in the free particle case, the position is not bound, so the wave function can almost exist everywhere, right, at the same time, and hence the probability of finding the wave function psi of x drops down to 0 under such conditions. If x tends to infinity, right, the probability should go down to 0. Right. So the Schrodinger's equation for any of for both these situations, we can always write h hat psi is written as, right, p plus p of x acting on psi of x should give you e of psi of x. So the solution of x, right? So all that matters for the Schrodinger's equation is the difference between the energy of the particle and the potential that exists, right? So you can always add or subtract some known constants to each one of them, so that anything which affects psi of x, and hence the probability to find the particle, and any of the observable which are operators which act on this particle, do not know about constants which you add to energy and the potential. For instance, if we define E hat is E plus some constant gamma, similarly V hat is V plus some constant gamma, right? You can clearly see that the Schrodinger equation does not get changed. So any of the offsets, so you can always offset the potentials by some constant value, and hence the energy, right? So that the total wave function does not get altered. So all that is important for us is the difference between energy, or energy offset by the potential, right? So in the case of bound states where E is always lesser than V, we take energy as negative. E is less than 0, and we put the potential to 0, right? Under such situations, you can clearly see that it is true, and we have just offset the potential by some, what is the existing potential value, right? And in the case of the other cases where E is not less than V, which is called as scattering states, we'll soon see what it means to be a scattering state. In the other cases, it's clearly E values are positive, and hence any of the solution to the Schrodinger's equation, which we again write as d square psi of x by dx square, is minus 2m by h bar square e minus v of x psi of x. So you can see that if e's are lesser than v's, right, so this entire value is going to be negative, and hence the k value, which is defined as minus 2m by h bar square e minus v, right, k square, we can call it k square, is real if e is less than v, and k square is negative and k is imaginary. Let's not have is k square, k is imaginary if E is greater than V. So the solutions psi, which is A e power kx plus B e power minus kx, which are solutions to this equation, you can clearly see that if E is less than V, then the solutions are bound in the sense that you have either exponentially increasing or exponentially decreasing. And if we take the wave functions should die at x tends to infinity, you can clearly see that the solutions will always be exponentially decreasing in any of these directions, and then the solutions will always be bound. You will see examples of this. If E is greater than V, then you can see that psi can be written as A e power I kx plus B e power minus I kx. I've just taken the I out of the k. Under these situations, you have propagating waves, and hence the solutions are called as scattering wave solutions. We will find examples of this as well. So now let's go and see one particular example which illustrates both of these situations quite convincingly, right? So let's go for an example. We will see a particularly special function which is called as Dirac potential. So what is a Dirac potential? A Dirac function, a Dirac delta function, is defined as delta of x, which is 0 at x not equal to 0, and is infinity at x equal to 0. This is how the function is defined, right? So if we plot it, it's like this: x tending to minus infinity and infinity. At x is equal to 0, it is an infinitely large line. I obviously cannot draw this, so I'm drawing it such that, let's say, this goes to infinity, right? And obviously this function is not normalizable, right? So if we integrate minus infinity to infinity, del of x square dx, in the conventional forms, this tends to infinity, of course, because at x is equal to 0, it is infinity. But what was taken is, Dirac defined this particular special function in this particular way, that any integral of minus infinity to infinity, del of x dx, will turn out to be 1. So this is called as a special Dirac delta function. Normal delta function, when you integrate it, it tends to infinity. But then a Dirac delta function is an approximation who says that if you integrate from minus infinity to plus infinity, this particular function, it turns out to be 1. It has some special properties. If you define a delta function to have this particular property, then any function f of x, when multiplied by this delta, x minus a. Of course, I think we all understand what is x minus a. So it means that the delta function goes to infinity at x is equal to a. And here, when we have defined it, it goes to infinity at x is equal to 0. If you define it x minus a, it is just shifted at a, right? Which will be f of a into delta of x minus a. So this means that this multiplication function will be 0 everywhere, and at x is equal to a, it will not be infinity, but it will be f of a, right? And clearly, integral f of x into delta of x minus a dx from minus infinity to plus infinity will give us f of a into integral minus infinity to plus infinity delta of x minus a dx, which will be f of a. So if we convolute any function f of x by delta of x minus a, then we get the value of the function at x is equal to a, right? So this function f of x can also be a constant if f of x is, say, alpha, Then we have a function which is called as alpha del of x. If we multiply it by del of x, we get alpha of del of x, and we define a potential alpha of del of x to be where a particle exists, right? So this is minus infinity to infinity. So alpha into del of x. So instead of this guy going to infinity, now this will be alpha, right? From the way we have defined it, any multiplication of a constant or a function into del of x should be f of a into delta. Instead of the function going to infinity, it goes to alpha now, right? And if we have a particle under this particular potential, depending on the value of alpha, now you can clearly see that there are different scenarios. So here at this is 0, right? So once again, like how we defined or how we solved our previous situations, we have two regions at x lesser than 0 and at x greater than 0. Both these situations have h bar square by 2m d square by dx square psi of x will be E of x, because the potential is 0 at regions less than x and regions greater than x, right? I have drawn it in at very bad scale, so you should assume that these values are very, very, very close to 0, that it cannot be noticed, right? So the solutions here can be written as a e power ikx plus b e power minus ikx, right? So obviously the solutions have to be imaginary, right? Because as v tends to 0, you can always have energies greater than v, so it has always to be imaginary. And k will be root 2m e by h bar, right? In the same way, you can also have for x greater than 0, the solutions are written as f e power ikx plus g e power minus ikx. Please remember that the f and g's are constants, and they are called like this for a particular reason. We will soon see why they are called in this particular fashion. Again, here also the k definitions are the same. So now to solve this equation, so basically we have two differential equations, and then we have four constants, four unknowns, including k. So how do we solve this? We need to have some boundary conditions and some initial conditions, right? The initial conditions are pretty straightforward. We will see that later on, but let's see how do we find boundary conditions for this. The first condition, which is typically imposed in most solutions to Schrodinger's equation, is the wave function is continuous. Continuous, right? How can we prove that the wave function is continuous? Do you have any clue? I think we saw this once in when we dealt with 614, but we can actually prove that the wave function should always be continuous. It can be proved like this. So we once again take the Schrodinger's equation. We are not taking this particular example. Let's take a general example, okay, and integrate it once. Will turn out to be minus 2m by h bar square integral e minus v of x into psi of x dx, right? And we integrate it twice. Psi will turn out to be minus 2m by h bar square over y e minus v of z psi of z dz. Of course, z and y are dummy variables which are just introduced to conduct these integrals. So now we have these two integrals. We can prove that the function has to be continuous. The first thing we assume, right, the function psi of x is square integratable in the sense that psi belongs to the Hilbert space, or in mathematical terms belong to L2, right? This is what we took. And the potentials also is also square integratable. So we are not talking about potentials which blow to infinity, right? Also belong to L2. If this is true, we can clearly see that integral e minus v of x psi of x should be lesser than infinity, right? How? By Cauchy-Schwarz, this should be lesser than integral psi of x plus integral the square of this, of course, e minus v of x square, right? This is Cauchy-Schwarz inequality theorem. So if we assume these two to be square integratable, this guy should be lesser than infinity, right? If this is less than infinity, you can clearly see that d psi by dx, that is the differential of the wave function, cannot go to infinity at any point, because the integral does not diverge at any point, and hence d psi by dx is always smaller than infinity, and hence d psi by dx always exists. So if d psi by dx always exists, that means the function psi is always differentiable. All differentiable functions are continuous. Right? So basically we have found, or we have come to a conclusion, that if you take the potential and the wave function to be square integratable, the wave function should be continuous, right? So what does it mean that the wave function is continuous? So we have two regions, psi of x, so something which exists here and something which exists here. At any point in time, you can approach the wave function from the left hand side and from the right hand side, and they should always be the same as the limit tends to that particular point, right? So psi of x tending to 0 from left should be equal to psi of x tending to 0 from right, in the sense psi of x is equal to 0 in the region 1 should be equal to psi of x equal to 0 from in the region 2. So this will be the first boundary condition that we will employ, that the wave function is continuous. Now for the second boundary condition, which is specific for this particular example, we have assumed the potential to be a delta function which is discontinuous, but still does not go to infinity, mind you, right? So this is v of x as x goes to infinity, just like this. This is alpha, right? So for this, all we have to calculate is what is the delta of d psi by dx, right? So let's take a look at the expressions that we have previously written. So that is d psi by dx is minus 2m by h bar square integral e minus v of x into psi of x dx. right? So all I'm trying to say is what happens particularly at x is equal to 0. What is a small change delta of d psi of dx at x equal to 0? How do we calculate this? It is just this particular value minus 2m by h bar square under a limit that some constant chi tending to 0 integral minus chi to chi e minus v of x psi of x dx. So basically this function or this integral tells you what is the value of d psi of x at some point, right? And I'm looking at small changes from that. And how do we find that small changes? You make what is the value of that at particular point and then tend to change that value very close to the neighborhood of that particular value, right? This is how we find small changes in a function. Now here it's easy to see that, okay, so minus 2m by h bar square, right? So this integral you can split it into two. Limit chi tending to 0 integral minus eta to e psi of x minus integral chi to chi v of x psi of x dx, right? Now as this function goes to 0, right, then psi of x, basically it will be psi of eta minus e into, right, psi of eta, and eta plus and eta minus are very small, right? So this particular value always tends to 0 if wave function is continuous. So this goes to 0 as wave function is continuous. So whatever is left is 2m by h bar square integral minus eta to eta v of x psi of x dx. And v of x is basically delta alpha into delta, right? And this is 2m by h bar square integral this alpha obviously comes out, delta of x and psi of x, and this will turn out to be 2m alpha by h bar square. Basically this product we saw previously is basically psi of this, and we are looking at limit tending to 0, so this will turn out to be 2m alpha by h bar square psi of 0. And this is delta d psi by dx at x tending to 0, right? So the second boundary condition that we derived is delta d psi by dx at x tending to 0 is 2m by h bar square alpha psi of 0. And for this potential that we drew, we had two solutions. One is a e power I kx plus b e power minus I kx on this side, and on this side it was f e power I kx plus g e power minus I kx on this side, right? So let's apply the first boundary condition, which will ensure that a plus b will be equal to f plus g, right? The first boundary condition is wave function to be continuous, so which is psi of x equal to 0 should be in the region 1 should be equal to psi of x is equal to 0 in the region 2. If you put x is equal to 0, all the exponentials vanish, so all you will get is a plus b equal to f plus g. And the second boundary condition, if we differentiate this and put it to 0, if you differentiate this, so delta is what? So at this point, at x is equal to 0, the delta is changes here, right? So I do, what's the change in, so the right hand side value is f into the differential of this is ik, right? Ik f e power ikx minus g e power ikx minus again ik a e power ikx minus b e power minus ikx. This is the differential, but then the differential has to be calculated at x is equal to 0, so which will give us ik f minus g minus ik a minus b will be 2m alpha by h square psi of 0, right? So now we have these two equations, equation number 1 and equation number 2. So with these two equations we can find two unknowns, but then we have a, b, c, d and k. So basically we have 5 unknowns. So how do we resolve this? So we have to also look at some special initial conditions. So we are going to assume some initial conditions. So let's assume, let's say that the particle is incident from this to this potential from left, right? So we have a particle from here, and then we have no particle which comes from the right hand side. And why do we see something like this in typical practical situations is that you want to check what happens to the particle trajectory if we have a potential. The delta potential is used here because it can be used to be generalized to any potential, any shape of the potential that we will show later on. But in typical examples, it will be like, so we have a particle which is almost free, particularly like in a crystal, we have electrons moving in a crystal, and then we have a defect at localized at some point. This is something like this. So the question would be, what happens, how does the defect affect the electron transport? And we solve this particular scattering potential, right? So in typical situations, we take A, which is the incident particle, to have a magnitude 1 because we want it to be normalized in comparison to amount of the particle which came in. So for instance, let's say we are talking about electron transport in this bulk and we have a scatterer here. We have a lot of waves which come here whose amplitude we take it to be A. The question is how much gets transmitted here and how much gets reflected back from this particular scatterer, right? So that is the general question that everybody wants to answer. So here if you see, we have A e power ikx, which is a positive moving wave. B e power minus ikx is a negative moving wave. I suppose you understand how I can say the positive k values are positive moving and negative k values are negative moving, because if we finally multiply it by the time dependence e power minus I by h bar t, we can clearly see that if we plot it, we'll see that the waveforms move to the right as time progresses if k values are positive, and the waveforms will move to the left as time progresses if k values are negative, right? So if we assume that to be understood, then A e power ikx is a right traveling wave, B e power minus ikx is a left traveling wave, so which is called as, so that's why A is called the incident wave and B is called as a reflected wave. F is a right traveling wave and G obviously is a left traveling wave, right? So F is called as a transmitted wave and G is an injected wave from the right. So this is injection from right. In typical scattering experiments, we assume injection from right to be 0. So we take G to be 0 and we take A to be 1. So we already lose two constants, and we take g to be 0, right? So we do not assume any of the wave is coming from outside, from this side, right? So with these two to be taken, we can solve these two equations, and what we will get is the b, the coefficient of being scattered, will turn out to be I beta by 1 minus I beta, and f, the probability to be transmitted, will turn out to be 1 by 1 minus I beta. And in this, we have used beta to be m alpha by h bar square k. So obviously these two equations are not very difficult to solve, right? So these are two equations. If a is 1 and g is 0, you can see that a plus b should be equal to f. And here you can do the same thing. So we will have two equations and three unknowns. So we can represent other two unknowns as a function of the third unknown. So k is an unknown. So we have represented b and f. B is the scattering or scattered wave amplitude, and f is forward transmitted wave amplitude. Right? So obviously while the scattering amplitudes are known, in quantum mechanics everything that matters. So basically with this scattering amplitudes, we can write the waves in the, let's write the waves. Okay, the incident wave is basically e power ikx. The reflected wave is I beta by 1 minus I beta e power minus ikx, and the forward transmitted wave is 1 minus I beta into e power ikx, right? But we know that, so basically these are psi forward of x, this is psi reflected of x, and this is psi incident of x. But the probability to find the particle to be reflected is obviously psi r of x square, right? So this will be integral minus infinity to infinity psi star r psi, right? And which will be integral minus infinity to infinity b square e power minus ikx into e power ikx dx, which will be just b square, right? Similarly, psi forward square will be f square. So b square is basically beta square by 1 plus beta square, and the forward transmitted is 1 by 1 plus beta square. So typically this is written as t, and this is written as r, reflection coefficient r, and t being the transmission coefficient, right? So the probability to be reflected back from a potential V defined by alpha into del of x is r is beta square by 1 plus beta square, and beta is basically m alpha by h cross square. So r is proportional to only alpha square, or proportional and alpha looks very similar. So all R depends on only alpha square. Similarly, T also depends on alpha square and not on alpha. So basically, the particle cannot differentiate if the potential is like this, positive alpha, or the potential is negative. This is minus alpha. So any particle here which is trying to cross a barrier alpha, obviously the intensity of alpha determines whether it is going to be transmitted at a higher probability or not, right? So for instance, let's say T is 1 by 1 plus beta square. So basically, higher the value of alpha, so T is 1 by 1 plus beta square. So beta is proportional to alpha, right? So higher the value of alpha, the T, or the transmission probability, is going to reduce, which is obvious and intuitive, right? Higher the value of alpha, smaller will be the probability to transmit, and higher will be the probability to reflect. That's understandable. But what's counterintuitive here is that the probability to transmit and reflect does not depend upon whether the state is a barrier or just a well. So for instance, a particle which is going here and which is incident on a well which has a potential or energy much lower than the energy of the particle can still be quantum mechanically reflected from the red curve, whereas classically, if the particle is incident on this red curve, the particle will just go through this barrier without being affected, right? In quantum mechanics, it tells you that the particle gets affected by a potential irrespective of the direction of the potential, whether the potential is attractive or repulsive. For instance, here the potential is a repulsive potential, so the electron wants to be or will be scattered back from this potential if the alpha is positive, and it will be attractive if the potential is negative, right? Typically, you would expect something to be accelerated as the particle goes through this, but it has an equal probability to be transmitted as well as to be reflected by this potential, the direction of this potential, right? So this is something new conclusions that the quantum mechanics drives. This has been experimentally verified in several places. We will see an experimental example of this in our course. But the quantum mechanical particle behaves in this weird fashion, such that it does not depend upon the direction of alpha, whether it can be positive, it can be negative, it can be any such, right? So now we have considered, let us take a situation something like this. Now let's see a different situation, or let us see the cases, or a case particularly similar to what we have seen in the red, right? So now let's consider this sort of a potential, right? This is V of x, and we have a particle whose energy E can be here or can be here. So in the previous case, we saw that the energy of the particle is higher than the potential, right? So that's what we have taken here, right? So here we assume the potential is like this. The energy of the particle is always higher than the potential, such as in this particular case. But here, let us see what happens if the energy of the particle is here, which is smaller than the potential. So if we write the Schrodingers equation, it will be h bar square by 2m d square psi by dx square will be E minus V psi of x, right? And d square psi by dx square is 2m by h bar square v minus e psi of x. So we are under the situation if e is less than v, right? So as we saw previously, only the absolute values matter. So if we take v to be 0, then we are talking about energies which are negative. So the negative energies that we will talk about now just does not mean that, just means that the energy values are lower than the potential that we are considering in this situation, right? In the general case, let's say whatever the potential is, we are offsetting all the potentials from the value of the potential here. So let's say if this is v, we're talking about energies which are smaller than v, right? And in this case, k, which is root of 2m by h bar square v minus e, is always going to be real, right? And hence the solutions are psi is a e power I kx plus b e power minus I kx, right? Now, if this is the solution, we have to talk about, let's say this is x going to minus infinity, plus infinity and minus infinity. And let me draw the potential in red. So our potential is somewhat like this. And the solutions are, let's say this is region 1, the region 2 as we have taken in the previous case. Both the cases the solutions are going to be like this, but it's not plus or minus I kx. This is just kx, e power minus kx, right? Because k values are real. And obviously at x greater than 0, a has to be 0, right? Because then the wave function explodes to infinity. So we cannot have the first term to be present in the regions greater than x greater than 0. And at x lesser than 0, obviously b should tend to 0. B should go to 0, right? So the psi can be written as b e power minus kx for x greater than 0 and a e power kx for x lesser than 0, right? So basically the wave function for this particular problem seems to be like this. It drops down exponentially from some value. So now we have to find both a, b and k, and as we have done previously, there are two boundary conditions, right? So we know that the psi of x at x lesser than 0 should be equal to psi of x at x greater than 0 in these two regions at x is equal to 0, which will ensure that a should be equal to b, right? And the second condition, that del d psi of x by dx should be equal to minus 2m alpha by h cross square psi of 0, will give us k should be equal to m alpha by h cross square. We just have to differentiate this particular value and then subtract it and make it equal to this value. You will get the solution of k to be equal to this, right? And when k is this, obviously the energy values to this is minus h bar square k square by 2m, which will turn out to be minus m alpha square by 2h cross square. One has to remember that in the previous case we did not have the negative here. If you're wondering about how the negative came, it's because we have offset everything. So the potential now which looks like this is actually offset, right? So the potential now looks like somewhere like this, because we have taken energies to be lesser than 0, right? So the potential is 0 everywhere, and at x is equal to 0 it is minus alpha. Instead of x is equal to 0, it goes 0 and almost infinity everywhere. It is just it is just reverse, right? So the actual v of x is basically minus alpha into del of x, and that's where you get, instead of v of x at x is equal to 0, psi of 0 getting 2m alpha h bar square psi of naught in our previous derivation, we get a minus value here, right? So we have found now k. Now remember, in the previous solutions we had infinite values of k's, right? So you always had n k, the k value were continuous. You can have several k values because they were all eigen solutions. There is plane wave solutions for x is equal to, for v equal to 0. But for the bound state, k value is unique. You just have one k value depending upon the alpha that you have, and for that k value you have only one energy value, right? So for the bound state has a unique solution, whereas the free particle state has infinitely many solutions. These are the eigenvalues of eigenfunctions of the Schrodinger's equation, right? So now we have to find, okay, so we have k, we know this, what are the values of a, we have to find the values of a. So how do we find the value of a? Is to normalize it, right? So if we put minus infinity to plus infinity, mod of psi of x square dx equal to 1, you will get 2 mod a square integral minus infinity to infinity e power minus 2kx dx, which will prove you that mod of a square by k equal to 1, which will show you that a equal to root k. So a is root m alpha by h cross square. I think this is just h cross, right? So the solution psi of x is root m alpha by h cross square e power minus m alpha by h cross square mod x, and the energy values are minus m alpha square by 2h bar square, right? So if I plot the bound state solution, this is root k, this is x. So we have found the solution for a bound state which is unique and has an energy which is described here, right? So in summary, if we have a potential which looks like this, at x is equal to 0, it is minus alpha del of x. If it has, let's say this is the potential v, right? If you have energies something like this, which is smaller than the potential E, there can be only one bound state, right, which has a wave function something like this, which decays exponentially from x is equal to 0. This is an bound state, and there is only one solution to this. And if we have energies greater than the potential E, so this is E lesser than V. And for E greater than V, you have infinitely many solutions. You can have many particle waves, you can have many plane waves which travel. And when they travel, you can have a particular probability of them being forward transmitted, and then it has a probability to be return transmitted, which depends upon the strength of the potential. But all that the quantum mechanics is saying is the wave which is incident does not know to differentiate between the fact whether the potential is a barrier potential or a well. Irrespective of that particular value, the strength is what finally determines how much gets reflected and how much gets transmitted, right? And with respect to this bound state potential, you can also kind of compare this with the square well potential, where you start shrinking the well, right? The distance 0 to a. Your ground state is like this, right? And you have excited states with energies going square of n, right? And this the smaller and smaller a that you have, the smaller width that you have, you can see that the ground state is going to get more and more narrow, right? And the energy values are going to be more and more separated. You note that the energy values are n pi square h bar square by a square. As a is small, the energy is going to explode. So in the limit that a is a very small value, the energy values are going to be so high, it will very quickly reach to infinity. So you can have only one bound state, and the bound state is going to be a ground state, right? It should have something like this. So at x is equal to 0, it is going to raise infinitely fast and going to fall down infinitely fast as well, right? So the bound state that we saw is just an extension of the infinite square wall potential, and in the limit a tending to 0, right? So with this description, we will just stop the lecture now, and the next time we meet, probably we will have a synchronous meeting the next time around, because we are going to talk about crystals and structures. I think it will be better to do it with a presentation. So we will have an in-person meeting next Wednesday, and we will solve your questions. We will resolve any problems that you have, and then talk about crystal growth and crystal lattice. Thank you.